Now let's first try to remember where we were. Well, I guess we have gone through compactness. Now that will be an important notion that we will continue dealing with in the sequel. But before that, we described the major problem concerning a topological structure as the formalization, the description of a point being arbitrarily close to a set. Now we have a rich enough structure to actually to formalize the distance of a point to a set in a metric space in general. And what we expect is, well, this distance should be zero in case a point is arbitrarily close to a set, which will yield us a new characterization of a limit point. Now let's start with that. Now for that we need a metric a non-empty subset of the metric and a point. Which is in the space. Now we will first form the set of all distances between this particular fixed point and all points in cap A according to the metric M. Now set D M, that will depend upon what the metric is, X A as the collection of all distances according to the metric M between X and any Y in A. Now, as A is non-empty, this will be a non-empty subset of reals. Will this also have an lower bound? Yes, well, these are all non-negative real numbers, so 0 is the lower bound of this set, where zero is a lower bound of dmxa. But then, by the infimum principle, this set has an infimum, which we will take as the definition of the distance of x to A. By the infimum principle, inf dmxa exists. So we define the distance of x to A with respect to M as M xa equal to the infimum of this set. So the first proposition is that this distance actually meets our expectations that the limit point, that a point x in this space will turn out to be limit point of cap A if and only if this distance is 0. Let Xm be a metric space A, a non-empty subset of X, and X in X. Now, X is a limit point of A if and only if the distance of X to A is equal to 0. Now, the proof of this is straightforward, and it's left to you. But what we'll need in the coming theorem is, well, what can we tell about this MXA if A is closed and X is outside cap A? Can it be 0? Well, if it's 0, X will be a limit point. But a set is closed if and only if it contains all its limit points. So if a point is not contained by a closed set, it cannot be a limit point. But in that case, this distance has to be positive. So let's note that simple conclusion as a corollary. Well, we again have Xm, a metric space, A, a non-empty subset, but this time we take X as a point from outside the set cap A. Now, if A is closed, then the distance of X to A, that will be positive. Now let's also note down the proof through which we have gone just a moment ago. Assume that A is closed as X is in X cap minus A, that is, it's not a point of A. X is not a limit point. A, since A contains all its limit points. So MXA is not 0. But what else do we know about MXA? It's the infimum of this set, but 0 is also a lower bound of this set. Since this is the greatest lower bound, this has to be larger than or equal to 0. Now, since MXA is larger than or equal to 0, we conclude that MXA is positive as claimed in here. This takes us to a theorem which is valid in Euclidean spaces, and most probably you're familiar with it. This is the so-called nearest point theorem, and this will turn out in the sequel to be a useful tool. Now this time we take a non-empty subset A of some Euclidean space. Now here, since anything else is not mentioned, we consider the Euclidean space with respect to its usual metric. And X a point in Rm. Well, the distance of X to cap A, we have that just defined in general in a metric space. This is well defined here as well. But now, if A is a closed set, then it will turn out that there is at least one point in cap A, say Y, such that the distance between X and Y is equal to the distance of X to cap A, to this set. That's defined as the infimum of a set. Well, this says the infimum is actually taken on by a point in the set. So the minimum exists. So that's simply that, but that will be useful. Now, if A is closed, then there is a point in cap A which is closest to X among all points in cap A. Then there is some Y in A such that the distance of X to A is equal to the distance from X to Y. Now we can also have a picture here. Say this is A, it's closed, so it contains its boundary. And X, of course, can also be a point in cap A. So it's any point in Rm. But if it's in cap A, then its distance to cap A will be 0, since this set here that will contain, if X is in cap A, it will contain the XX, which is 0, well, then the infimum of a set of real numbers, which are all non-negative. If that set contains 0, then 0 must be the infimum. So let's first take care of that simple case. Now, let's start by assuming that A is closed. First, consider the case where X is in A. Well, then, simply taking Y as X, then this will be a point in A. We have dxa, which is 0, is equal to dxy. Now consider this case. Now assume that X is not in A. But now we know that dxa is now something positive by the corollary above. Now, if we add something positive to that positive number, to the distance of X in A, and if we consider now the closed ball about x, then this will have, if it's closed ball, then this will be contained in the set. Then this will have a non-empty intersection with cap A. If the radius of this closed ball about x, if that's larger than the distance of x to A, will have this non-emptiness. But the increment which we added to dxa in forming the radius of this, now we can make that smaller and smaller. Well, then we'll have something smaller, which will have a smaller intersection. And well, if we continue that ad infinitum, that is, if we take a sequence consisting of positive numbers, a decreasing sequence converging to 0, and add the terms of that to dxa, form the sequence, then what will obtain in the limit as the intersection of these intersections? Now that's promising to give us the candidate of a closest point of cap A to x. Now let's do that. So, well, if we need some decreasing sequence of positive real numbers converging to 0, we usually take for that the sequence 1 over n. Well, it's not a must. You can take any one, but that's the simplest. So for each k in n, set bk equal to, well, in fact, I can directly formulate this intersection instead of taking the ball first and then intersect it. Let this consist of all, let me write y, because x is a particular fixed member of Rn, y in A, such that this will be the center, dxy, its distance from x is less than or equal to the distance of x to cap A plus some increment which we take as 1 over k in this case. Now firstly, by definition of this is the infimum of distances of points in cap A to x. Well, if I take something larger, by the very first proposition we had at the beginning of the course, the intersection of that with cap A will be non-empty. So A sub k is non-empty since 1 over k is positive, and by definition of dx cap A as the infimum of the relevant set. So let me write that. Note that for each k in n, bk is non-empty. Is it closed? Well, consider this as the constant sequence. So the sequence, all of whose terms are equal to dxy, and this as a sequence that depends upon k. But if for each k, this inequality, well, given a k, if this inequality holds for all y in here, and if I take a sequence yn in bk, which is convergent, the limit will also obey this inequality. Okay? If zn is less than or equal to wn for each n, if both Zn and W are convergent, say with limits Z and W, Z is less than or equal to W. Here, let me write it and check that BK is closed. Is BK bounded? Yes. Any epsilon ball is bounded. Here we have a closed one that's bounded as well, and this is a subset of that. And bounded. So what can we tell about each BK? Compact by Heine-Borel theorem. But also, note that for all k in N, we have that BK plus 1 is contained in BK. Why is that? Because 1 over k plus 1 is less than 1 over k. So this is a nested sequence. Moreover, we know in particular B1, which is the largest set among all BKs, because this will be 1, that's the largest diameter in that case, is compact by Heine-Borel theorem. But then the BKs, they are all closed subsets of this compact set. Do they satisfy the so-called finite intersection property? Well, if we take finitely many BKs, assume that E is a finite, non-empty subset of N. Now, if I take the intersection of BKs when K is in E, can you tell what this intersection will be equal to? Well, we take the largest number in E. Say if it's L, this will just be BL, because B1 contains B2 and so on. And this is equal to BL, which is non-empty, where L is just the maximum of E. But B1 now, let me rewrite this. BK, K in N, is a non-empty family of closed subsets of B1 with the finite intersection property. But since B1 is compact, what does this imply? That the intersection of BKs over the entire family, that is for all k in the set of natural numbers, that will be non-empty. That was the third characterization of compactness. Since B1 is compact, this implies that the intersection of BKs K in N is non-empty. But going back to this picture which we have constructed at the beginning, well, we said, well, we can make this 1 over k smaller and smaller, but a point which is contained in all these sets, that is in each bk, after the formalization, that's a natural candidate for a nearest point of cap A to x. So let's take any y in here and check that it actually is a nearest point. Of course, it need not be unique. Well, in fact, if, for example, we have the points on the circle, that's A, and if you take the center as x, every member of cap A just goes on the circle. Well, they're all closest to x, so everything to the other extremes, every point in cap A might be the closest point to x. But we're not interested in uniqueness, we're only interested in the existence. Now pick any y in this intersection. Well, then, firstly, y is in A, because these sets are all subsets of cap A. Okay? On the one hand, by definition of these bk's, for all k in N, we have that y is in bk, so y satisfies this inequality. dxy is less than or equal to dxa plus 1 over k. But what does this imply about the relationship between dxa and dx cap A? Well, again, we can use just if a sequence component-wise, term-wise, dominates another sequence, then the limits obey the same inequality. Here, take this as the constant sequence. Well, its limit is itself. And consider this sequence. Its limit is dxa. Then, dxy is less than or equal to dxa. But in order to complete the proof, we also need the opposite inequality. But what do we know? Y is in cap A. So in fact, dxy is a member of the set whose infimum is equal to dx cap A. Well, let me write that in full. On the other hand, dxy is a member of ddxa, because y is in A. So, the infimum of this, in particular, the infimum of this set is in particular a lower bound of this set. So, infimum dxa, that's less than or equal to each member in this set, in particular dxy, but this is just the definition of dxa. So we have this together with this, thus dxy is equal to dxa. So we have produced a nearest point in cap A to x. Now, suprema and infima, in case they are not taken on by a point in the set whose supremum or infimum you consider, well, that always causes some problems. But if they are taken on, if they're respectively the maximum and minimum of the set, well, then things are smoother and simpler. So this, in that sense, will be useful. If A is closed, we will always be able to find a nearest point. So that completes this section. But what we have done in this section, it's not closed, confined to itself. It will be used everywhere. Now let's remember what our aim was when we first defined compactness. Now we said if we have a finite set, a real valued function on that set, if that finite set represents the options, the alternatives available to an agent, and U is either the utility or the disutility that our agent enjoys when those alternatives materialize, well then it's very nice that our agent has, it would be very nice if our agent has some optimizing option, some optimizing alternative. But in the case of finiteness, the maximum and the minimum will always exist, and so an optimizing agent will have no difficulty in deciding what action to choose. But finite sets, they're very restrictive. Well, in fact, in economics, well, most of the sets, well, say the set of all available commodity bundles, they're infinite, so can we extend finiteness to a notion where functions, real-valued functions defined on such sets will turn out to possess a maximum and a minimum, respectively. But we can put also certain smoothness, regularity conditions on the function. Now we have the compactness as an extension of the finiteness of a set. Now let's get now to the function side and let's see what kind of particularities a function should possess in order to possess a maximum on a compact set if the function is real valued all the time. So that takes us to 1 point something. I don't remember the number. It's continuity.